simplified version of the theory was presented this morning. So we're only going to be considering those two equations and not the additional cofactor and determinant of deformation gradient. So all the theory is summarized in this top section. So feel free to read through this at your leisure. Most of this was covered this morning. It's just a slightly more simplified version for this tutorial. So the main objective of today's tutorial is to run this conservation formulation in MoFem using the Petrov-Galerkin formulation. So this module in MoFem is fairly new and still under development. So we do have some limitations on what we can do. So most of that is described in this document at some stage. But if you do have any questions, just let me know. And if there are any bugs or errors, also let me know, and we'll be happy to look into those at some point. So I'll just scroll down here. So in this tutorial, we can consider two different constitutive equations, one being linear elasticity and one being annealing compressible Neo-Hookean, which are presented here and here. In the code later on, we have a flag so you can swap between whichever model you would like to use. For the examples I'm presenting in this tutorial, you should see very little difference between the two. But if you want to run different geometries or more complicated examples with this code, you're welcome to change those parameters and see if there's any difference. So as he presented this morning, here's a summary of the stabilized Petrov-Galerkin formulation, just for the linear momentum equation and deformation gradient tensor. And I would just like to draw your attention to the stabilization parameters, which we will have a play around with in this tutorial. So you'll be able to see just exactly how important they are. So those two parameters are our tau f here and our phi f here. So as Ian presented this morning, if we were to use tau is equal to 0, we'd recover standard Grubnov-Galerkin formulation, and you should see that it's unstable. One of the tasks later on is to do that, and you'll see exactly what happens. And then another task is to have a look at how she plays an important role as well in the simulations. So one important aspect or limitation that we have with our current implementation is that our explicit time integration will only be forward Euler at the moment. Ian presented this morning that he generally uses multi-stage Runge-Kutta time integrators. At the moment, we haven't implemented that in MoFem, but it's currently a work in progress, and we're hopefully going to get that implemented very soon. So one important aspect to consider here is that our time step, our delta t, is going to be governed by our CFL and our mesh size over our wave speed. So in the examples that I'll present in a minute, I have set the mesh size already to run fairly quickly. If you start to refine the mesh too far, the delta t will start getting even smaller, and then it would take significantly longer to run. So that's just a warning for this tutorial, at least. If you have, when you are able to get this image on your own in a Docker container and you have more cores, you might be able to run it faster, but we are limited with our computational resources at the moment. So I highly recommend running the examples in this notebook just as they are first to see what happens effectively, see the results, investigate some differences between this formulation and standard finite elements. So firstly, we're going to consider a simple example to benchmark this new formulation effectively. And in this case, we're going to run a simple, effectively one-dimensional bar with a sinusoidal traction at one end, and while it's fixed at the other end. So it is modeled in full 3D using linear tetrahedral elements and linear shape functions. As Ian said this morning, the whole point of this formulation is to go low order with both mesh and shape functions to obtain fast solutions for these fast events effectively. So this example here, our traction is just going to be pulling along in our x-axis with a sinusoidal function, which is defined here. And that has a given analytical solution as shown here in equation 19. And later on, when I run it, you'll see that they'll plot against each other and we can see the difference between the two solutions. So as with the previous tutorials, I suggest that you play around with the mesh size a little bit. I have a cell later on which is coded so that you just hit run and you'll be able to see the difference with mesh sizes. So it's up to you if you change the mesh size yourself or play around or just leave it as it is, really. So I'll just run a couple of these cells so we can show you what's going on. Oh, I didn't run the first one. I had the first one hiding. So just make sure you run this first cell here because it was hidden for me. And then you can run the second one again. Oh, no, I didn't like that one either. There must be another hidden one. Ah, there we go. This is the first one we need to run. And then we run this one. Then we run this one. All right, so you shouldn't see any errors come out at the bottom here. So this cell here is the most important one since it is actually setting up our problem. And in my case, I've set the length of the bar equal to 10, which is shown in the table above. And then our Y and our Z directions are set to 1. So we have our 3-dimensional bar. I've split our two element sizes, one for along the axial length and one along the thickness and height, because we are effectively running a 1-dimensional problem. The only real important parameter is our element size across the axial length. But you can play around with either, and examples later on will do that. And then I just set the material parameters, boundary conditions, just like we have done in previous tutorials through Gmesh. And then I set various solution parameters. So as Ian discussed this morning, our stabilization parameter tau is just set to whatever our delta t value will be. In the next example after this, you'll be able to change that and see what happens. And the same again with xi. So you'll be able to play around with that, see what happens for some of these examples. And then we just have a Boolean flag for our traction. So for this first example, we're considering a sinusoidal traction. Second example, we consider a constant traction, which is a shock or a discontinuous problem. And we'll be able to see the effects that has on this solution. So the other parameters in this file aren't too important. The only other one I would consider highlighting is this one here, which is the location that will be plotted in post-processing. So I've selected here just roughly the midspan. So it's at the bottom midspan, but you can play around with this location and you can see what the value is at different locations. The analytical solution should update as well, so you'll be able to see how close the approximation is. So I'm just going to quickly run the mesh. So you can see here we have our 3-dimensional bar. So the traction will be applied to this end, and it will be fixed on this end. And in this case, I only have one element across the thickness and 10 elements along the length. So it's a very coarse mesh. But we'll see in a second that when we run MoFan, it should run fairly quickly. But since this is a time problem, you'll see that it produces a lot of outputs and a lot of steps. So for some of the later examples, they will take time to run, but you'll notice that it is running because the log file will be scrolling as you are waiting for it effectively. But after it's run, we'll be able to see some of the results. So that's it finished now. So I'm just going to convert the results and visualize the plot. So since these are dynamic simulations, everything is defaulted to plot as just GIF files. So we can't rotate these. But since it is a 1-dimensional problem, I've set it up so that you can effectively see what is going on. So in this case, you can see that our left end is fixed and our right end is being pulled with a traction. So because it's a sinusoidal traction, you can see that over time, our bar is extending and contracting based on the deformation. And if we plot our displacements and our velocities, at the location that I picked, which was the midspan, we can see that the MoFem solution, even with one element across the thickness and 10 along the length, we match up fairly closely with the analytical solution for both displacement and velocities, which makes sense since they are connected. So I'll let you run this example yourselves. So this one will just refine the mesh along the axial length, and you'll be able to see whether the solution converges to the exact solution. And similarly, the third task is refine only along the thickness, and you'll see what effect that has. So I'm not going to say what's going to happen, but you should see what happens. So once you've run that problem, we have a second, or part B for this problem, where you'll play around with the stabilization parameter. So in this case, I've set the two values to 0, and you're free to change these parameters to whatever you feel like, and you can plot different scenarios if you'd like. So if I just run this example quickly, we'll be able to see exactly what happens. So in this case, since our stabilization parameter is now set to 0, we are, instead of running a Petrov-Lurkin, we're effectively recovering our Bubnov-Lurkin approximation. So what we'd expect for this to happen, or for the solution in this case, is that it will blow up almost instantly. So as you can see here, our solution just goes completely unstable within 10 seconds of our simulation. So if you play around with our tau parameter, you'll see that depending on what value you select, you'll have a change in when it becomes unstable, with values around delta t being the best. And you'll see it'll be very stable around those times. So I'm not going to run the second example, but I'll just explain what it is. So it's exactly the same problem setup, but in this case, we're just pulling one end with a constant traction, which is a discontinuous shock problem. So you should see oscillations in the solution, and I'll let you run it, and you can see that for yourselves, what happens. And again, I've just provided templates for all this section with the task to compare elements along the length, or refining elements along the length. And you should see a similar result to the one above. And lastly, we have a bending example. So in this case, so the first two examples in this tutorial are just effectively benchmarking our solution against analyticals, while this third one is to demonstrate why this formulation is an improvement over standard displacement-based formulations. So in this example, we're just going to bend our beam by pushing down on one end, and it should deform downwards. And for low order tetrahedral elements, standard displacement finite elements will lock. And if you run this example, you will see locking occurring in the standard displacement formulation. I'm not going to run this just now because it does take some time, so feel free. So I think at this point, feel free to start running the examples yourselves. If you're starting into any errors, just let me know. I'm happy to help. And everything should be described in the tutorial notebook. Does anyone else have any comments or any questions? Probably just one thing to mention is I do highly recommend running from the start through the notebook, because there are multiple examples, there are some definitions which need to be run first, and sometimes they aren't picked up if you don't run them all in order.